All right, let's jump right into it. Parametric equations. I know, they can look a little intimidating when you first see them, but I promise, by the end of this, you're going to see they're a super powerful and totally doable part of calculus. We're going to break it all down, step by step.
So think about your standard graph, like y equals x squared. It's great. It shows you the shape, in this case, a parabola, but it's just the path. It doesn't tell you the story of the journey along that path. It can't really show you direction or speed or time, and for that, we need a whole different kind of tool.
And that tool is parametric equations. So instead of y just being a function of x, now both x and y are functions of this third variable, a parameter we almost always call t. Just think of t as time. It's like a director for the graph, telling the x and y coordinates exactly where they need to be at any given moment, tracing out this beautiful curve as it goes.
Okay, so even with this new parameter t running the show, one of the most fundamental questions in calculus is still the same. How do we find the slope of the curve at any point? We are still on the hunt for dy dx, the good old slope of the tangent line.
So here's the big question. How in the world do we calculate dy dx when both x and y are busy depending on t? We can't just take the derivative of y with respect to x like we used to. We're going to need a new game plan. And here it is. This is our formula. It turns out the slope, dy over dx, is just a simple ratio. It's how fast y is changing with respect to t, that's dy over dt, divided by how fast x is changing with respect to t, which is dx over dt. It's really just the chain rule in disguise. And if it helps, you can kind of think of it as the dt's just canceling out.
Let's actually put this rule into practice. So here we've got x as ln of 4t minus 3 and y as 2 over t. First things first, we find dx by dt and dy by dt all on their own. So dx by dt is 4 over 4t minus 3, and dy by dt is negative 2 over t squared. Then you just divide them, pop in our value t equals 3, do a little simplifying, and boom, our slope is 1/2. See? Not so bad?
All right, finding that first derivative. Pretty straightforward. But now we've got to talk about something that trips up so many students, the second derivative. You know, the one that tells us about the concavity of the curve?
Now, it's totally natural to think the pattern would just continue, right? I mean, if the first derivative was just a simple ratio, shouldn't the second one be just as easy? What would your gut tell you to do here?
This is the trap. It seems so logical, doesn't it? Just take the second derivative of y with respect to t and divide that by the second derivative of x with respect to t. I mean, it feels like it should work.
But it is absolutely 100% wrong. Seriously. Doing this will get you the incorrect answer every single time. It's probably the single biggest mistake people make with parametric derivatives. So, what is the right way? Well, this slide shows us the real deal. The second derivative is the derivative with respect to t of the first derivative that you already found. All of that divided by dx dt again. You see that? That extra division by dx dt at the end, that's the crucial step everyone forgets.
Let's just break that down into a simple three-step process. Step 1. Find your slope, dy over dx, as a function of t. Step 2. Take the derivative of that entire expression with respect to t. And step 3, the vital last step, divide that new result by your original dx over dt. Whatever you do, don't forget step 3.
Okay, let's see this thing in action. So in this example, we first find dy dx, which simplifies down to 2 times 3 to the t. That's step 1, done. For step 2, we differentiate that with respect to t, which gives us 2 times ln of 3 times 3 to the t. And for that final, crucial step, we divide that whole thing by our original dx dt. Look at that, a bunch of stuff cancels out perfectly, leaving us with a nice, clean final answer of 2.
So we've got the mechanics down. But what can we actually do with these derivatives? Well, one of the coolest applications is finding the exact points where a curve has a horizontal or a vertical tangent line. And the logic here is actually wonderfully simple. A horizontal tangent line means the slope is 0, right? Well, for our fraction dy over dx to be 0, the numerator dy over dt has to be 0. And for a vertical tangent, the slope is undefined. For our fraction to be undefined, we have to be dividing by 0, which means the denominator dx over dt must be 0. It really is that simple.
Of course, finding the value of t where this happens is only half the job. To get the actual coordinate point on the graph, you have to take that value of t you just found and plug it all the way back into your original equations for x and y. Whew, that was a lot.
I know, but you've totally got this. We've just built a complete toolkit for tackling derivatives of parametric equations. So let's do a quick-fire recap of the essential formulas you need to lock in. And here they are, all in one place. The first derivative, your slope, is the ratio of the derivatives. The second derivative, remember that one has the extra division by dx over dt. And for your tangents, just remember, horizontal means the numerator is 0, vertical means the denominator is 0. Go ahead, screenshot this, write it down. This is your ultimate cheat sheet.
And that's really it. You know, like anything in calculus, this just becomes second nature with a little bit of practice. You've learned the rules, you've seen the common trap to avoid, and you know how to apply it all. Keep practicing, and you are going to master this stuff in no time. Good luck!